Hello everyone, my name is Miles Karim, and in this video I'm going to talk about current mirrors. So here's a list of topics. We're first going to go through some intro and motivation for current mirrors. Then we're going to talk about some of the design trade-offs that we often encounter while designing current mirrors. And then we'll discuss some of the current mirror topologies, right? So the basic two transistor current mirror, the simple cascode current mirror, a low voltage variant of the cascode mirror, and then a regulated current mirror and a self-regulated current mirror. And then we will talk about the systematic mismatches in the current mirrors and the random mismatches. We'll also discuss the Pilgrim's law. And then finally, we will talk about some of the layout considerations for the current mirrors. Now, that's a lot of stuff. And so instead of making one large video, I just wanted to split it into different parts. So I've mentioned 3 or 4 parts where I'll be discussing each one of those topics. Now, it might be that you already know coming into this video, you already are aware of the current mirror topologies, and so maybe you want to miss part 2, right? Or maybe if you want to see the random mismatches and the Pilgrim's law, maybe you should watch part 3 and 4. So yeah, basically whatever it could be likely that you already know about current mirrors to some degree, and so based on that, you could just choose whichever parts you want to watch, or if you're new to current mirrors, it will be good to watch all the parts. Okay, so let's start off with the intro motivation and the design trade-offs, and I'll discuss the basic two transistor current mirror in part 1, so which will be this video. All right, so I'm using let's see, I'm using Razavi's this Zoom. I don't know if it's not gonna show, but it's yeah. Basically, it's Razavi's book, edition 1 and chapter 5. You could have any other edition as well. Also, there's Gray Mirror. There's all sorts of other books. Current Mirror is a very basic and a very standard topic for analog design, and so you'll find a bunch of resources online as well for current mirrors. Okay, so let's start with the intro. We are trying to implement a current source, and we're trying to mimic an ideal current source, and basically this doesn't exist, right? This in real world does not exist, so we have to make it somehow, and current mirrors, as it turns out, would be a good way to realize this ideal current source. Now let's look at some of the properties of an ideal current source. Let me ask you one question. For an ideal current source, if you have a lot of noise at this node, let's say, the voltage at this node, let's say Vx, so this is node X, right? The voltage here is changing a lot. And let's say this current should be I naught. Should I naught change if there's noise at node X? If the voltage at node X is changing a lot, will I naught be constant, or should it be constant? And the answer is yeah, it should be, right? That's basically an ideal current source. It maintains a precise current regardless of whatever the voltage is at, let's say, node X, right? And so in other words, I could write it as for a small change in voltage, how much does the current change? So that's the derivative, and the current should not change. So the derivative should be 0, right? And that means basically the transconductance of an ideal current source is 0, which, as transconductance is the inverse of the resistance, so I could say the output resistance is infinite. So if the transconductance is 0, the output resistance is infinite, right? Or in other words, you could also say like resistance looking into this node here, our out, that's the output resistance of the current mirror, would be infinite. And that basically is just another way of saying that whatever the voltage is across this ideal current source doesn't matter. The ideal current source will maintain a current I naught regardless, right? And so that's a very important feature of an ideal current source. And as it turns out, when we discuss current mirrors, we're going to talk about this R out being infinite, and and how close can we get to this ideal behavior of a current mirror, and we'll talk about output resistance for sure when we will discuss the different topologies of current mirrors. So I just wanted to lay it out there right now. All right, let's talk about some of the design trade-offs for current mirrors. So I could think of six. First, again, is R out. As we just talked, R out is infinite for an ideal current source, but as it turns out that we won't be able to get an R out of infinite, but we'll try to maximize it as much as possible. So, and while we do that, we pay a price. And so some of the other trade-offs, one of the most common ones is the voltage headroom, or the V out headroom. We typically, for a lot of cascode mirrors, once we go through the other parts, we'll find out that we are often trading off R out for the voltage out headroom or the V out headroom. So those first two are pretty important, and they'll come up again and again in our discussions for current mirrors. All right, the next few are the capacitance or the bandwidth of the current mirror. Now you might think like, well, current mirrors are low bandwidth circuits. True, but what if you have a current mirror that's an active current mirror? So for example, the first stage of a 5-transistor OTA, right? You would have something like this, right? And then you would have this current mirror on top. And again, it doesn't have to be a PMOS, it could be an NMOS current mirror as well, depending on how you design the first stage. But regardless, it would be some sort of a current mirror. But here, the current mirror is not just biasing or sending in bias currents, it's also processing the small signal voltage, right? And so in this case, bandwidth of the current mirror would be important. But maybe the bandwidth for some other current source may not be important if it's just like providing a bias current. But in case where the current mirror is processing the small signals, that's where the bandwidth is important as well. And so that's one of the trade-offs that we'll find out. The absolute magnitude of the output current is also one of the trade-offs. The PVT variations is also something we will discuss about, and the output noise current. The noise in a current mirror is also a trade-off. So let me just, so now I want you to think for each one of these different parameters that I mentioned, like 6 of them, for an ideal current mirror, for an ideal current source, what would be the values, or what would these parameters look like? And you can pause the video here if you want, but yeah, so essentially, this is what an ideal current source would look like, right? Or an ideal current mirror. We realize a current source, an ideal current source with a current mirror, but regardless, R out would be ideally infinite. The voltage headroom would be infinite. The capacitance or the bandwidth would also be infinite, ideally. The magnitude of the I out would not matter. You could draw or source currents and the nanoamps, the femtoamps, or amps, regardless. You would have the whole range, and you can just have whatever I out you want, ideally. PVT variations, nope. They won't be existent, and the noise current will be 0. So that's ideal. And obviously we don't have that in the real world. So, but it's good to know what are we, what's our goals, right? Because if we're trying to build current mirrors, we want to possibly like achieve some of these ideal parameters, or try to get as close as possible. So anyway, here's a little diagram of how those trade-offs work. So let's say here's like a brief summary, right? So let's say voltage V out headroom, right? So here now to increase let's say V out and V out headroom and R out. So let's say one of the very common things to increase R out is to use a cascode current mirror, right? And so while that increases R out, we pay a price in terms of the voltage headroom that decreases in current mirrors. So you're trading off R out the output resistance with the voltage headroom. Another pointer here for the trade-offs would be the size of the transistors in the pyramid. So for example, maybe you want a higher R out and you're thinking, well, I need to increase the length of the transistor, and so that improves the R out, right? And or you could be like, I need to increase the magnitude of I out, and so I'm just going to a bigger transistor, bigger W by L. So okay, well, what kind of price would you potentially pay for a bigger size transistor, right? The parasitic capacitances of the transistor would increase with size, and so if you have a bigger width and length, basically parasitic capacitances like CGS and other capacitances would increase, and so the bandwidth of the perimeter would decrease. So in this case, you would be potentially trading off R out or the magnitude of I out with the bandwidth, right? So that's another trade-off. And okay, well, another pointer here. Let's say you want to increase the magnitude of I out. Right now, GDS is directly proportional to the drain current and lambda. So if you're increasing the I out or the drain current of the output transistor, then the GDS also increases. And if GDS is increasing, then output resistance is decreasing. So here you're trading off. There's a bit of a trade-off with output resistance and the magnitude of I out, right? So in this sense, there could be other ways you could think about like different trade-offs in the current mirror. This is just a few examples that I wanted to show. And then again, there's other things that we'll talk about, the PVD variations and the output noise current as well, and how those are traded off with the other quantities we have mentioned here in a big picture. Okay, so let's talk a little bit about the motivation. Oh, by the way, if you're new to current mirrors, by the way, you might find that this whole talk about the design trade-offs may not make any sense to you, and that's okay. As we will progress through the videos, the parts of the videos, I will be discussing these trade-offs in more detail, and you will find out that how these trade-offs are relevant to each current mirror topology, and yeah, basically, it's okay if you don't understand it, but this is just like a summary that after you learn about the different perimeter topologies, you could come back to this diagram and see for yourself like how these quantities are traded off in different perimeter topologies. Okay. All right. So let's talk about a little bit of motivation for perimeters. We start off. I don't know about you, but to me, when I was learning or taking my analog design course, this was like just one of the topics that came up, and we just on a random day we started learning about perimeters, and I didn't quite understand why, right? And so it's sometimes good to just go back to the fundamentals and see like why do we actually need a perimeter. So to kick off the discussion, I would say here's a basic example, right? So we're trying to mimic an ideal current source that, let's say, draws or has a current I naught. Let's say I come up with this solution. I have a transistor M1, and then I set a particular VGS based on a resistor divider. So that's my resistor divider. Let's say this is R2, this is R1, and that's the VDD. Okay, and that's where the current I out comes from. That's the output current. And if I want to mimic a current, an ideal current source with I naught, I'm basically going to design this circuit. I'm going to choose R1 and R2, and I'm going to design the M1 transistor accordingly, such that this I out is equal to I naught, the same as this I naught over here. So this I naught over here. Okay. So great. Now these two, I'm making a bold claim here that I have achieved this current mirror with this circuit, right? It has an I naught, And so let's start looking through it. So the output current of this transistor M1 would be given by something like this, right? Mu n Cox W by L, VGS1 minus VTN, which is the threshold voltage, squared, and then 1 plus lambda VDS. So one thing here is that I'm assuming that I'm parking my transistor M1 into saturation first, right? And so I'm using the saturation equation over here. And then yeah, so that's basically I out, and my goal was to set it equal to, let me just use the width here. So my goal is to make it equal to I naught. So, let's say mu n Cox would be a constant. So I set W by L here to something, and I set VGS1 to something. I know my VTN while designing, and so based on that, I can set these two quantities such that the I out is equal to I naught. Okay, so great. I have designed a circuit that has that basically sources I naught current. Okay, another thing we talked about is a current mirror, a current source, an ideal current source having infinite output resistance. Okay, so let me draw a very quick graph of this transistor M1, VDS versus ID. And this is a very familiar graph. You would have seen it multiple times, right? Let's say this is the line, and this would be, let's say, saturation, right? And so what I'm saying is that I'm going to bias this transistor such that it is in saturation, and the current in this saturation region would be whether I put my transistor here or here or here or here, whatever the operating point might be, the output current you'll notice is I naught, right? So, okay, what we see from this graph is that VDS can change, and as long as the current, as long as the M1 transistor is in saturation, then VDS can change, and my current, the output current of this circuit would still remain I naught. So sounds to me like we have achieved this condition as well. Oh, sorry. Change in current due to a small change in voltage is zero, because look, I can be anywhere on this line, and my current remains constant regardless of the voltage change across this transistor, right? So that sounds to me like an infinite output resistance. So I've made a circuit that that sources I naught current, and the output resistance is infinite. Great. Okay. So are we done yet? Like, is this it? And if we are done, then why do we need this whole discussion about current mirrors, right? Is this is this circuit not enough, right? So let's start dissecting this circuit, and start to think about what potential problems can happen in this particular circuit if we really want a precise current through this node, which is I naught. So what could go wrong in the circuit? All right, number one, the mobility of the transistor. We thought of it as a constant, but is it really? Turns out that mu n of a transistor will change or will vary based on temperature. And so, if this circuit is, let's say, on a chip, and that chip is in a car, and that car is in Calgary, and Calgary is in peak winter, so minus 35 degrees Celsius. So you have this circuit that is exposed to a minus 35 degrees Celsius temperature, you would get a mu n, which is different from mu n or mobility at 25 degrees Celsius. Or you could be in Dubai, right? You could be at plus 45 degrees Celsius, peak summers, and so you'll get a different mobility, right? And so if the mobility changes with temperature, then I out will change, right? Based on temperature. And so is that something we really want? No, right? Because we said that an ideal current source would just source I naught current regardless, right? And regardless of the temperature as well. So looks like our circuit here is not going to draw I naught current, and it might change. It might, it might draw a different current than I naught in cold temperatures, and it might draw a different current at hot temperatures. So there's variation with temperature because of this mobility, depending on the temperature. So that's first thing. What about VTN, the threshold voltage of the transistor? So it turns out VTN also depends on temperature. It also depends on the process. So, well, the threshold voltage of the transistor can change wafer to wafer. And so later on, we will talk about how, even VT on the same chip, of transistors on the same chip might also vary, but that's a later discussion. For now, you need to know that the threshold voltage will change with temperature as well. So again, if you have this circuit, you have this M1 transistor and it's operating at a hot temperature, it will have a different threshold voltage. Cold temperature, it will have a different threshold voltage, and so it won't be drawing the I naught that you had designed for in whatever design tool that you used, right? So that's a second variable. And so, okay, let's talk about VGS here. So VGS is is basically depending on this R1 and R2 resistor divider multiplied by the supply, right? So let's talk about this R1 and R2. We know that this is a ratio, so that's good. But then let's say if we have multiple copies of this circuit, right? Is there a possibility that R1 and R2 will have different ratios, or will have a variation if you have multiple copies? Yes, right? So that will mean that there would be a VGS variation. And because there's a VGS variation, again, the I naught will have the output current of this circuit would have a variation as well. It won't exactly be I naught. So now we have talked about VGS as well. Another thing, VGS. VGS is also, you can see here the VGS. VGS also depends on VDD. So you might think VDD is constant, but imagine this scenario. If VDD has a bunch of noise, which is actually something that's common, supply rails have a noise. And so if there's noise on VDD, then this node will also have a noise, right? And if this node has a noise, that means that there's noise, your VGS is noisy. And so if VGS is noisy, then the output current here would be noisy. Is that something that we want? No, right? We want a very precise I out is equals to I naught, but it seems like VGS will also vary because of the supply noise and because of the resistor variation. So VGS is not trustable either. It will vary. And so, yeah, and so that's like point number 5. That's point number 6. So that's all I could think of for now, but I'm sure there's more things in this circuit as well. Once you start brainstorming more ways on how this circuit can screw up. And so, yeah, suffice it to say that if you're designing this circuit, hoping that, it would work under different conditions, temperature, voltage, process, and it's going to draw a very precise current that is I naught, like an ideal current source, then that wouldn't be the case in practice. And so, which is why we will see, the point of this exercise of like dissecting the circuit and seeing whatever is all the things that could be potentially wrong with the circuit is that once we start discussing current mirrors, we'll try to solve some of these problems, right? And so you'll see how, or the things that we are doing in current mirrors to combat with some of these variations. Okay, so let's start with a very basic current mirror. So here we have transistor M1 and M2. I'm sure you have seen this before as well. This is IREF and this is I out. Right, so we have M1, which is a diode connected transistor, and M2, which is the output, the transistor in the output branch. And so here we have VGS1 is equals to VGS2, and if we have that, And the aspect ratio, the sizes of both the transistors, the W by L of M1 and M2 is the same, then the I ref and the I out would be the same. So let me start writing out some equations. Again, this is assuming that all the transistors are parked in saturation. So here it would be mu n Cox by 2, W by L 1, VGS 1 minus VT 1 third 1 plus lambda 1 VDS 1, and it would be the same for M2, except all the subscripts would be 2 now. So we'll have a W by L2, VGS2, VT2, lambda 2, VDS2. Okay, so if we divide these two equations, this one and this one, we basically get something like this, right? And let's start looking at this. So mu n changes with temperature, but if we have a ratio of the two mu n's, then assuming that mu n dependency of temperature is the same for both of the transistors, then this would cancel out. Okay, and then VGS, any variations in VGS, and then a VTN as well. So temperature variation on VTN, let's say, because both transistors are close to each other, we say that they're exposed to the same temperature, and so their threshold voltages will be affected in the same way. And the VGS is also like, we tied both of them together, so VGS of those two transistors should be the same. So in other words, this term and this term should be equal. And so these can be canceled out. By the way, we will learn later on in part 3 or part 4 that the threshold voltage of the two transistors can actually just have variance due to random mismatch. That is something we'll discuss later. But for now, we're assuming that the overdrive voltages of both M1 and M2 would be equal. And so a ratio of those both will cancel out. And so we're left with an expression like this. We have the width over length ratio of both transistors, and then we have 1 plus lambda 2 VDS2, and then divided by 1 plus lambda 1 VDS1. Okay, so let's start thinking about some of the things that we have achieved with this current emitter. If you look at it, is this expression dependent on mu n? No, right? We don't see mu n in this expression. So that means that the I out of this current mirror would not depend on mu n. And so we have achieved this part. No effect of mu n due to temperature variation. And then again, same thing for VTN. You don't see threshold voltage in the final expression for the two transistor current mirror, right? So we have sort of suppressed the effect of VTN dependency as well on temperature. Now, let's start thinking about some of the downsides. Here, what could still cause an error in this current mirroring operation? Well, we still have this term here and this term here. Both of these are not necessarily equal. VDS over here, that's VDS1 and VDS2. These are not necessarily equal, right? And so if we have some sort of lambda effect, if lambda 1 is not equal to lambda 2, then these two terms will not cancel out, right? And this, if these are not canceling out, then they will add some sort of error to this current mirror operation. So you might say, okay, well, one of the things would be to just increase the length, right? Increase L1 and L2, both of them, so that lambda 1 and lambda 2 are as small as possible, right? And so if lambda 1 and lambda 2 are as small as possible, then the effect of VDS1 and VDS2, because it's getting multiplied with lambda 1 and lambda 2, would also be something small. So one thing we could do is increase the length of the transistor so that these lambda 1 and lambda 2 would decrease. That's first thing. And then, but is there a downside to that? Okay, let's start thinking about that. If we increase the length of the transistor, then we would have to increase the width as well if we want to keep the current ratio the same. So let's say if I increase this length to 10L and this to 10L, right? Then I would have to basically make a width, increase the width by a factor of 10 on both the transistor as well to maintain a permeable ratio, right? So I'm basically beefing up both the reference device and the output device. And so is there a potential downside to that if we have larger devices? Bandwidth, right? Bandwidth would decrease because you have larger transistors with more parasitic capacitances. So that's one thing. And yeah, and so basically with this two transistor current mirror, VDS1 is not equal to VDS2, which can introduce errors in the current mirror. Second thing is that you want to make lambda small, which means beefing up both of the transistors, increasing their size, but then bandwidth suffers. So that's also another disadvantage. Or I wouldn't say it's a disadvantage, it's something that it's a design consideration. Maybe bandwidth is important to you, maybe it's not. So depends on what you're trying to achieve with this current mirror. But anyway, layout area would be one of them, right? If you're increasing both the transistor sizes if you're increasing length of both of the transistors to achieve a smaller lambda, then you're basically increasing the layout area. So that's also a thing. Now, R out of this transistor, that's pretty simple. Looking into this node here, we see a drain. And so this would be 1 over GDS2. That's pretty straightforward. The voltage headroom would be just whatever voltage is needed to keep M2 in saturation. And so that's VOD2. And so the minimum Vout needs to be at least VOD2 or something greater. Okay, so that is the two transistor current mirror. We talked about the motivation for why we need the current mirrors. We also talked about the trade-offs for current mirrors, and we talked about the intro, like some of the basic characteristics of an ideal current mirror. So yeah, we discussed this, and this here. And so in the next part, we'll be discussing some of the more interesting current mirror topologies. And so that's pretty much it for this video. It's supposed to be short and simple. So yeah, thank you very much for watching, and I'll see you in the next one. Bye-bye.